Analytical groupies, this is Dr. Gosher. I am in my office, and as I promised, I would make you a little video explaining some of the stuff to do with our overlapping spectra. So this is all about what to do when you have multiple compounds whose spectra overlap with spectrophotometry. So what do I mean? First of all, we've got the issue of maybe one of your compounds has a spectrum like this. Okay? Maybe the other compound is a little bit different wavelengths. So remember, spectrum is wavelength versus absorbance. And we will scan maybe, I don't know, let's do UV, 210 to 350 nanometers. What'll happen is when both of these compounds are mixed together in the same sample, for lab purposes, maybe this one is caffeine, because we're talking about our soda, and this one is benzoic acid. That when these things are mixed together, you're going to end up with a spectrum that is an overlay of the two. It'll be something like this. And in that case, then you have to do a little bit of math to figure out how much we have of each thing. The important thing to remember is that Beer's law, which you know, absorbance equals absorptivity times path length times concentration, that this is so-called additive. So if we have two different compounds, we've got compound 1 at concentration 1, compound 2 at concentration 2, then we're able to understand that if we've got one thing in the solution and another thing in the solution, that their different absorptivities, their different concentrations will add up to this total absorbance. So here's where things get tricky. This is the absorptivity of your first thing. It's characteristic of that. And that's the absorptivity of the second thing. So you need to be able to find out what the absorbance is of both of these. Easy way to find out absorptivity is to have a standard. So you have in your labs the various standards. Simple thing, take one standard. We know concentration is 20 milligrams per liter of caffeine. Okay? We want to find out what is epsilon. Okay? So you go in, you say, I'm using a 1.0 centimeter cuvette, your liquid. Can make that cute, right? So it's cuvette. And that's going to be times the absorptivity. So this is concentration, path length, absorptivity is our unknown. And we're going to measure the absorbance. And maybe you get a number. Maybe you get 3. No, 3 is bad. That's too high. Maybe you get 1.5. Okay. You can just rearrange and solve this for absorptivity. If you do that once, then you have a number. If you do it multiple times, it's much more accurate. So you guys have made concentrations ranging from 4 milligrams per liter all the way up to 20. And you're actually going to make a calibration curve where you have concentration of, for example, your caffeine here, and then you have measured absorbance. And you'll get dots. And if it follows Beer's law, which is saying that we have a linear relationship, and absorbance is on Y, concentration is on X, then this becomes a Y equals mx relationship. And the slope of this trend line ends up being m, and that is your absorptivity times your path length. It turns out that the cuvettes that you guys used were 1 centimeter path length, so you're able to get epsilon from your calibration curve. Now, let's go back over here. Sometimes you have this nice situation where the two component spectra are pretty well separated. And you can see that there's a region where one is absorbing more and a region where another one is absorbing more. So you take your scan of your benzoic acid and you say, here's the peak wavelength for that. And I'm going to call that, I don't know, wavelength 1. And over here you say, well, this is a different wavelength for caffeine. That's wavelength 2. And you do these measurements of absorbance at those. So maybe this is 230 nanometers, approximately. This is 270. Then over here, this will be the absorbance at 230. And it'll give you then the absorptivity at 230 nanometers. Excuse me. Okay, Now what do? You do this 4 times. You're going to have the absorbance at 230 for benzoic acid as well. You're going to have the absorbance at, well, what did we say, 270, the other one, for caffeine. And the absorbance at 270, your second wavelength, for benzoic acid. So we know how both of these things behave at both of the wavelengths. One wavelength is described for one compound, one is described for the other. And then by this, we're going to have these plots. Beer's law is followed if they're linear. You get the slope of each of them, and it brings out your different epsilon values. Now, you measure your soda. And you say, soda absorbance here, soda absorbance there. And I'll say, well, I want to work at 230 nanometers. Working at 230 nanometers, I measure this absorbance and I put it right there. And I say, soda comes out at 1.732 absorbance units. I know what my slope is. Okay, so this is at 230. I know what my slope is for benzoic acid. So I take this epsilon 1 at 230, put it in there. Path length is the same, concentration unknown. Okay. Plus, now the absorbance of caffeine at 230, take that epsilon. So absorptivity for compound 2 at 230 nanometers, same path length times the concentration of caffeine. Also unknown. And we say, well, crap, what are we going to do? We have 2 unknowns but 1 equation. But aha, says the math goddess, if you measure here and you come out with a different absorbance, then we can say, well, the absorbance at 270 was 1.981. I don't know. I'm just making numbers up, you guys. And then you go to your other 2 graphs for that wavelength, and you'll say, here's the absorptivity from this. Now it's absorptivity for compound 1 at 270, the slope of that calibration curve. Same concentration here. We don't know what it is, but we have the same concentration. Take our other absorbance now for caffeine at 270. That's the slope of this particular calibration curve, so compound 2 at 270. These numbers are just an index, if you're keeping track. Same concentration of caffeine there. Now what you have is 2 equations, the 270, the 230, with 2 unknowns. Your unknown is concentration of benzoic acid, concentration of caffeine. With algebra, you can rearrange the 2 equations and 2 unknowns and plug them in. Now, if you guys go to your textbook, and I am flipping through my printouts here, what it will show is this page, and it's page 421. And right down at the bottom, it's what to do when 2 spectra are well resolved. This is the theory of our lab. And the theory of our lab is we have 2 spectra well resolved. And here, they just came up with the same thing. 2 equations, 2 unknowns. They show you how to use matrix algebra. And it is your choice whether you want to solve these 2 equations, 2 unknowns by hand, or whether you'd like to follow their example and do it with matrix algebra. It's also possible to solve these equations in Excel using this kind of a format, where you're going to come up with, here's the absorptivities. Okay, so absorbance, like the 1.72. Okay, so this is the absorbance at the first wavelength. This is the absorbance at the second wavelength. So here and here. You've got your unknown concentrations of compound X and Y. We've got the absorptivity times the path length that go in. And you rearrange it into matrix math. And you say, well, and if you don't know linear algebra, just follow the positioning. The 2 absorbances go from there to there, and you bring down these 4 absorptivities, and you set it up. And then what you'll do is you'll go to the next page in the textbook, which I didn't print out, and you'll type stuff into Excel and follow the directions. That's it. Now, what happens if you don't have a nicely separated sample? What we just described was the bottom half of figure 18.1. where we have a region that's unique to one thing and a region that's unique to the other. Unique means, okay, this absorbs a little bit here, this dark line, but really it's mostly from that compound here. Over here, the absorbance is mostly from this compound. That's when you do what I just talked about. Well resolved. If your spectra are not well resolved, and you've got this kind of a thing, where there is no one really unique thing, no one really unique wavelength, then what you'll do is you'll pick multiple wavelengths. Instead of 2, instead of this unique one and that unique one, you'll say, okay, 5 or more wavelengths. Here's the example from the book. I have titanium and vanadium mixed together. Vanadium looks like this. Titanium looks like that. And the mixture of the two is really hard to tell apart. So just like before, you're going to scan one standard alone, one standard together. I'm telling you about this because there's a homework question. And this is a really powerful thing. And what we do is we guess. So the math that goes forward is purely about guessing. It's like, well, I've got a blob that looks like that. And I know that one component is this, and one component is that. If I just arbitrarily say, okay, 2 times that plus 3 times this, I'm going to get some spectrum. So this is a guess. And you can plot that, and the guess will be like, okay? Not perfect, not what this is, but it's a guess. Then you compare this guess, which is comprised of some portion of a known, so this is standard A, and some portion of another known, standard B. Because we're adding up with Beer's law, we can do this. And this is our actually measured sample. We say, well, if I compare my guess to the real one and keep adjusting the 3 and the 2, maybe I do a little bit less of that and see, do they match better? Maybe I do a little bit more of this, do they match better? Eventually you're going to fit some weighting, the 2, for example, of that, and some weighting of this in order to fit this curve. Oh, great. This is called least squares fitting. It literally is just a process of guessing and then seeing how well does your guess fit the data. The least squares fitting, so we're on page 420 of your textbook, is described a little bit better there. And there's an Excel sheet. You have the 5 wavelengths, okay, which you chose, and that's these 5 wavelengths here. So that's a wavelength, that's a wavelength. You have the absorbance of the standards. So this is measured. It's a standard A, standard B. And then you have a measured absorbance of the mixture. You don't know the concentration of the things in this mixture, but this is a real measurement. That's your measurement here. And then, just like before, because it is our theory, our fact that things add up, okay, we still need the epsilons. In order to get the epsilons, well, you need to know the concentration of the standard so that you know here. And you use that to calculate epsilon for the standard at each wavelength. Then what we do is we guess. So this is our guess. And it'll tell you cell G6 is here. This is literally saying I'm going to take my absorptivity times some, I don't know, guessed value. What's the guessed value? We're going to input some hypothetical concentrations. So I'm going to guess that the concentration of titanium is 0.001. So it's absorptivity of 678 times a guess plus the absorptivity at that wavelength, we work on the wavelength here, of vanadium, 172.5, times a different guess. Okay, so here's vanadium guess. We don't know what it is. They're probably not equal to each other. And that's going to spit out some estimated absorbance. The result of that goes in this column. So all of this is estimated absorbances where you use the same hypothetical, we're just guessing here, concentration times its path length. You can set up an equation, a spreadsheet, see if you can get these things back. And then we want to compare. Here's our guess, and here's the actual thing. Not the same, right? So we say, well, to get a really good fit, I'm going to take the difference between here and here, and I'm going to square it. So absorbance calculated, that's this, minus absorbance measured, that's that, squared. So this is where we get least squares fitting. Square the differences between your guess and your actual measurement of the mixture. Then add up all the squares, and we want to make this number as small as possible. So make the residual small. Thus it is now least squares from the square. And then the fitting is, the measurement is going to be some combination of this standard plus that standard. I'm going to keep guessing concentrations to fit into this equation. I don't know what this is, I'll guess. I don't know what that is, I'll guess. And you can fiddle around with this. You can type in a number, see if the sum goes up, which is bad, or if it goes down. And then you can type in a number here. Does the sum go up, which is bad, or down, which is good? Or you can let Excel do that for you. Remember the data analysis stuff for our lab? We also have so-called solver plugin. Go to your Excel, go to options, go to add-ins, and then down at the bottom there's the manage add-ins. And you want to check solver. Then when you go to data tab, this will be over on the right hand side as an option. It'll pop up a box. Your box will look a lot more modern than this. My box is kind of old and ghetto. But you'll say, by changing these cells, and you'll click on your two guesses, okay? By changing those cells, I want you to minimize, it says min, the value where? Well, I want you to minimize this value. So set the target cell. We want to minimize this sum of squares. So we say solver, minimize that value by changing simultaneously both of these. And then we say solve. And it'll go through the computations. It'll raise one, lower one, figure out is it making this number bigger or smaller, and in the end it'll minimize the squares and say here are your two concentrations. You fit it. Voila. Now I know this is not intuitive, right? I recommend that you guys give it a try. Work through the examples in the textbook using Excel and math. If you need a tutorial on solving the simultaneous operations here, keep watching. If you don't, go ahead and leave. Real quick, let's just say you didn't want to do the matrix math, okay? So you can totally do this matrix math, all right? That'll fix you up. But if you don't like that, what'll we do? Well, we have to solve one of these. Algebra. Let's choose arbitrarily to solve for concentration 1. That means we need to have one equation where concentration 1 is the only thing that shows up, right? So concentration 2 here needs to disappear. We want that to go away. So we find a way to get rid of it. You solve the second equation. So we want to substitute. In order to do that, solve the second equation for C2. All right, so we got to subtract this. We'll do the absorbance, 1.981, minus that thing, which is your absorbance for the other compound, path length, concentration 1 that you don't know. Okay, so I'm moving that to the left side. That's going to equal our second thing. But I actually really want this alone. So I'm going to divide that out, 1.981 minus EBC, that's keeping our wavelength indicator, divided by this epsilon. That equals concentration 2. Now this whole thing can plug in right there where this is, and you're going to end up with one equation. I'll write it small over on another piece of paper. How are you loving the video so far? Dry as a piece of stale bread, I know. Okay, so I'm plugging this crap into here, getting out one equation, one unknown. We're trying to solve for C1, so we need to only have that. Okay, we leave the original information about this in here, and then instead of C2, we plug in all of this stuff for C2. And this isn't too bad because by now you actually have a number for path length, you have a number for your absorptivities, so a lot of these symbols go away and they're replaced by your numbers that you're used to. All right, one equation, one unknown, which is C. Do a bit of algebra. You'll pop out what concentration 1 is, and then you'll go back and you'll say, oh, here's a number, random number, 25, okay. Pop in 25 into the second equation here and solve for C2. All right, guys, good luck. Enjoy the video. Email, come by office hours for questions. Practice. Hasta la vista.